are looking at. That sort of that sort of thing. That's why I haven't insisted about it, because it's not super. I don't find it super important, but at the same time, like nice. We are all. Not many people are reading this book and this. Now, the very all the people in the universe that I know are reading this book are in this. Meetup, right? So very occasionally, one might have a comment or an idea or a question. There is not really like it was like a very idle comment. I don't even remember what it was. I only remember that it will waste all of our time to talk about that thing in the meetup, right? It was one of those things that is like an idle comment, like fun, pseudo fun thing. So
yeah. So have you used any sort of permanent chat before? I guess Slack is pretty popular, and I've participated like a couple of times on some Slack channels where there's some.
I'm actually part of several communities on Slack. So it's I also in IRC. I use both. I'm in communities in both IRC and Slack. The problem with IRC is that you have to be there, right? That it's if nobody's connected, then nobody will know what you were going to say. But Slack is a little more asynchronous. You just throw a comment, and 2 days later, somebody have an opinion about it, and just ping it, sort of thing. No, I don't have any strong opinions, one way or the other. Oh, you have a okay. Let me join to the IRC right now.
Anyone else have any opinions or thoughts on whether this is something that they may use sometime?
Well, my thought. Sorry, there goes the train. My thought on Miguel's use case there was he had something that was sort of interesting, but he didn't want to derail the meetup about it. Mm-hmm. And my thought on that is, like, we're not making a ton of progress anyway. Feel free to derail the meetup if it's interesting. Let's talk about it. So.
Yeah. I mean, you can always bring anything up. So, and we have lots of time, and so far, I have no problem going over time. So as long as people stick around, that's okay. But I do see the point. Like sometimes something just occurs to you outside the meetup, and then you may not remember it, and it's nice to have that thing right at your fingertips. And have it
was sort of. I mean, I had the beer ready, so it was a sort of a moment that you are in the 2 beers. You had 2 beers. You're reading the art of computer programming. After that night, the question no longer seems to be reasonable anymore. Yeah, I literally don't remember it. I don't remember what it was.
Right.
I just remember that it was fun.
And especially
I felt it was fun.
Especially with TAOCP, I mean, this happens to me all the time. Like I'll make a first pass or maybe 2 passes before the meetup, but then it's really during the meetup where I'm really focused on it that a lot of thoughts occur to me. But we do have a certain agenda that we need to cover, and so then I'll think about it more, and then over the next few days, more thoughts will occur to me, or I'll do some work like I wrote the C program for topological sort, and I really appreciated a lot of things that I don't think I really sort of paid a lot of attention to the first time around. So yeah, I would definitely use it. So as long as there are people there, so you can count on one person being there. And the Freenode people were really nice. I've never really used IRC in a very, very long time, at least 20 years. So I'd forgotten pretty much all about it. But yeah.
I have used it I have resumed using it for the last few months. And it's kind of nice. I mean, it's all automated. I'm also always in, so it opens when I start my computer and automatically joins the channel. So I'm going to be present to always.
Okay, that's great. So we can keep the conversation going. I think that's really the basic thing, is to just keep some conversation going outside of some more structured or organized events. And and I like the fact that it is open source. It supports open source projects. So that's really attractive to me. Okay, so speaking of topological sort, there were a few things that I was thinking about since the last meetup. And I don't know if you remember, we didn't cover this last paragraph in that section, but Knut says that he's going to cover an even better algorithm in section 7.4.1. But so far, as of August, he's only up to section 7.2.2.9. So it's really hard to say when this 7.4.1 is going to come out and what the context would be. But I assume that it's going to be something more combinatoric and graph based, because that's what that chapter is all about. So it would be interesting to find out like what papers were published, you know, maybe in the few years just before the third edition came out, related to topological sort, and how it could be more efficient. A couple of other things that I was thinking about was how could this algorithm or the problem be parallelized or distributed, if you wanted to throw some more computing power at it, and also an incremental or online version of topological sort. So where you've got the relations coming in, you know, in a stream, like real-time stream, and you're supposed to do the ordering, you know, online while you're processing the input. So one relation comes in, you do a topological sort of the existing relations, and then another one comes in and it may change the ordering. What would that even mean? Like, if you've already started a task that depended on something, and then a new pair comes in that says, you know, the task that you started has a new dependency or a new prerequisite, how would you deal with that? So a lot of interesting thoughts, and a lot of these are sort of applicable to any algorithm that we'll be seeing. So any thoughts on this? Did you also have any sort of ideas about what we covered?
Well, I missed that, so I was just looking at I assume this was pages 261 to 270, 271-ish.
Yeah.
Does anyone feel like giving a quick summary of what algorithm T is actually doing for the top one?
Sure. Anyone?
I feel like I'm vaguely familiar with union find, and I'm wondering if there's a version of union find that works to do a topological sort. But I only thought about it in the last 10 seconds.
Yeah, so it's kind of weird because the algorithm itself is obviously DFS, right? The highest level possible interpretation of the algorithm is literally DFS in a way. Just
do you just want to summarize the problem first, Miguel? So
yeah, let's try. Let me try to do that. So the problem, I think the problem begins when you have a bunch of nodes or objects with links to other objects, but not necessarily in a linear way, right? So your data structure, ignoring the encoding of it, it's a graph with links like
something like.
That's exactly right. Yes, exactly. So yeah.
And then we're trying to linearize it into.
Yeah. So, and the question is, I mean, it's a partial order. So you cannot tell always what. Sometimes, like when the example of 4 and 8, they are both before 6, but not necessarily in the same order. Sadly, I haven't reviewed this after we talked about it, so my memories have to come slowly. So the way Knuth is creating in order to create such a graph, the input data is a list of pairs, where each pair is an edge, right? From number X to number Y, there is an edge. That's pretty much it. And the order is the first element of the tuple is the source, and the second element of the tuple is the destination. And then the big idea, apparently, if I remember correctly, is figure 8, where sequentially, so as an array, we're going to, so we know we have n elements that we're going to load, and we don't know. I mean, I don't remember if we know how many. I think so.
Yeah, so that's the first pair in the input is that special meta pair, and the first entry of that pair is going to be 0. The second entry of the pair is going to be the number of objects.
Right. So the big idea is that we're going to be adding sequentially a sequential list where the actual value of the list is the number of objects that are below that one object, right? For example, the number 1 will have 0 children, or not necessarily children, like a number of elements below it, right? No, adjacents, not children in general, just literal, the next, how many immediate children do they have? And it's essentially an adjacency list. And the key is that because they are sequential, then you can just by knowing the index, you can find the address very quickly, right? Because there is no, you don't have to iterate over them. You know the index, and you just find it. And then the algorithm plays with that. We'll have to read the algorithm. I don't have the algorithm in my head. The whole point is create this adjacency list of a graph. I guess we all know how that looks like. And from there, the idea is that you will follow the zeros. So you do a first pass. You find all the nodes that have no adjacents, and those are the first ones. And then there is a step 4. Then there is the step 4 where we update everything in a very clever way and very confusing way, because there is the same name using for the same adject. And once you read it and you understand it, it's very cool, but then you forget it very quickly. And that's what happened.
Yeah. I think I've got it now.
Yeah.
Looking at it, he's got
it's hard to remember, at least in my case.
So he's got a picture of what the structure looks like, except that it doesn't have the thing you were just talking about of using the count field to mean 2 different things. He doesn't actually ever show that in diagram form. But yeah, I think.
No, but I remember that we had, at least for me, it was a little bit confusing, because it's like we had the adject, the linked list connected to each node. I'm like, okay, but it's linked. What's the deal? And the whole point was, these are just the adjacents. So it's just a list. It's the only one way of having a list. What really matters is that the nodes that have the count that are sequential, the rest can be just anywhere.
Yeah, so Michael has sort of summarized what happens when the input is processed. You end up with that figure 8, I think it is, and so you've got a count for each of the objects of their predecessors, and you've also got a list of their successors. you end up in that place, and that's where the sorting actually starts. So a first pass is made to find all the objects that have a count of 0, means that they're independent of anything else. So you can start with those, and so you put them in a queue, and then for each one of those items in the queue, you start popping them. And as you pop each one, you go through there, the popped items successor list, because now it's been taken off the list of items, and then you update, decrement essentially, the count, predecessor count of each of the successors. And then as each count, as any count turns to 0, then it gets inserted into the queue. And so it's a way of avoiding like repeated scans, and it's essentially like a 2-pass algorithm. There's one initial pass through the entire array of objects, and then it's essentially just going through the queue, popping and inserting. So yeah. So for today, we've got circular lists, and it's a relatively short section, so I'm hoping we can get through it and then have some time for exercises. And then finally, like this optional post main session segment where I'm going to walk through the program, the MMIX program for one of the algorithms. And yeah, and so I think that's about it. So the application for today is arithmetic on polynomials, so which would be addition and multiplication of two polynomials in a few variables. In the text, he uses, he assumes that there are 3 variables, but in the demo program, we can go up to 4. Okay, so we are at page 273 in section 224, and we'll have about 5 minutes till about 2:28. Has everyone gotten through the section? Okay, who can summarize?
I'll give it a
Thanks.
So he's talking about circular linked lists, which is where you basically have a linked list, in this case a singly linked list, right, with next pointers, and what we would call the tail of the list doesn't have a null pointer as its next. It goes back around, and if you follow the next pointer from the tail, you get back to the head, and so you can go around forever. He's got an interesting thing here, which is when he represents it as this linear, like left to right list, where the head is at the left and the tail is at the right, he keeps his pointer PTR in figure 1 pointing to what I would call the tail of the list.
Yep.
Because if you have a pointer to the tail, it's really easy to get to the head, but not vice versa. So that actually makes a lot of sense. And if you have a pointer to the head and you're trying to get to the tail, you have to walk across the entire list to get there. But from the tail to the head is always one step. And he talks a little bit about what do we do for empty lists. Reintroduces the underflow concept, where if you're trying to remove something from an empty list, then that would be an underflow. And the thing that I put in the chat, which we can talk about later because it's a little bit of a digression. And he talks about one other way of representing the circular list, which I'm not 100% sure of the distinction he's making here. But he's saying you could have a designated list head node that I'm assuming would store the first element.
No, it would be. It would be. I'm not sure if the list head is a regular node, but there would be one extra node that would be like a sentinel node. So the structure would look exactly the same, but it wouldn't have actual data in it.
Right. Which ends up being very similar to his first diagram, except that instead of having PTR point to the tail, this would be like having PTR point to the head, because the pointer you have access to is the next pointer of the list head object.
Yeah, to start off, like PTR would be the list head in some sense.
Well, his figure 4 doesn't have PTR anymore. He's got
it doesn't. I was just sort of trying to reconcile what your view is related to PTR, but yeah, there is no PTR. You're right. It's just there's a list head.
Yeah. So he sees this as a very different thing, even though I'm not really sure what the benefit of that is.
So the benefit is in that last line of the paragraph. Like, one advantage is that the circular list will then never be empty. So you don't have to deal with an empty check. It's a sentinel. No, it's like, you know that if that's the only node that you encounter, then the list is empty.
Yeah, but you still have to do things like, if they're trying to remove a node from an empty list, you can't let them do that. And you can say, oh, but my list is never empty. It always has size at least 1. But that just pushes the problem to, well, now you can't let them remove a node from a size 1 list. So I don't really see entirely what that's buying. Maybe you don't have to deal with null pointers anymore. So none of your equations are going to involve this lambda that he's using to represent a null pointer.
Well, you can't delete the sentinel. So presumably something in the node, like if it's polynomials, maybe everything is 0 and you know that that's the head. So you can't delete that one. Instead of saying you can't, instead of having to check the size of the list, and then if the list is 1, say overflow, you just check the value that's already there. It's going to be a little bit easier. And then the other thing is that if you're processing it, a list with a sentinel, in the general case of a circular list that came before that, you really have to check the address. You have to compare the address each time. And like he points out, even that may not work because you may have deleted something in the list as you were going through it. So it's kind of hard to check that you've come around back to the beginning. But with a sentinel, you start at the next one, and when you reach the sentinel, you're done. Starting at the next from the sentinel is really starting at the first node in your list.
Yeah.
It is an alternative. So I think that the dilemma that anyone would be facing when they read the two things is like, is there a clear-cut benefit of one over the other? I think Michael has summarized the benefits, but I think you can work everything either way. So, but yeah, and from what I've sort of understood so far and seen so far, Knuth really likes sentinels. In a lot of his algorithms, he seems to prefer something that is like processed routinely, and it's a sentinel, rather than have some other special different kind of structure that you're looking at. Hi, Jay, you just joined. I think that you've joined before, but if you're new to the group, could you just tell us where you're connecting from geographically?
Yeah, hi. I'm from the West Coast of the United States.
Okay.
And yes, I have been lurking here. I'm sorry. I just wanted to see what you guys are on right now, so I can get caught up.
That's great. So we do have the videos of all of the sessions. If you have a chance, you can catch up that way as well. But yeah, it's great to have you here. Do you just want to go by Jay, or?
Yeah, that's actually my name.
Oh, okay.
Yeah.
Nice. I just see the letter J, so that's why I don't.
Got it. Yeah.
Okay,
my name
cool.
is J, J-Y-J.
Okay, so let's continue. Did somebody else have any questions or comments on what we just read? By the way, Arthur, I don't remember if you read the piece about the avail list and how that the double-edged arrow that he's using. Do you know what that means?
Yeah, the double arrow was from way back. That's swapped.
Okay.
And the avail list, I forget if I was here if it was specifically discussed, but it's a free list of nodes.
It's a free list of nodes, yeah.
Nodes from and putting them back onto. Yeah.
So double edge, all that's saying is that there's more than one simple operation involved, and he's just sort of summarizing maybe 2 or 3 steps that's involved in either getting a new node, allocating a new node, or freeing an existing node.
Although the avail thing is also, so the way I understood from the last bit, so like philosophically is the list of available nodes, but when we saw it in practice, it was more like once is the available nodes that we free, the space that because when you start with the linked list, before in the book, you start with avail empty, right? So you start adding stuff.
Avail shouldn't be empty, because avail is just it's representing the storage pool.
Yeah.
So I mean, maybe in your scheme somehow avail is the null pointer, although I don't know how that would make sense.
No. So let me explain again. So I remember in this algorithm that was mentioned in the book earlier, when you actually do start with avail empty, like null, but you reserve a space for linked lists, right? And every time, so you start with the available empty, and you take a space from the sequential empty space that you're supposed to have. And if you delete a node, then that deleted address goes to avail. No, no.
I think what you're referring to is the scenario where he said you may want to have different kinds of lists sort of coexisting in some
Yes, exactly.
block of
Like a more
memory where
generic
you
way
have
of using avail. That's
a
what I meant.
region that's for sequential allocation, and there's a region for the linked or dynamic allocation, and how you could, detect sort of the boundaries between them.
Yeah.
But avail is just saying that this is some storage pool of nodes, and you may need to deal with the fact that that pool is limited in capacity somehow.
Yeah, exactly. What I'm remembering, what I'm trying to say is that right after he says avail is the linked list of available nodes, right after that he says, but that's very inefficient. You should not try to link all the available space before work. That's not practical. That's just like is a more of the artifact for thinking about available space. Like the available space should come from some place that you know that is available. But in practice, you would not have all the available space actually linked, right? You need some algorithm to create available space in a way that is efficient.
Yeah, that makes sense. I think that's fair enough. Okay, so let's continue with this. We're just going to read one paragraph, which is really just describing the problem. And I only want to spend like a minute on this, and then what I want to ask all of you is, how would you solve this problem? Just whatever comes off the top of your head, like your first reaction to solving this problem, what would you do? Okay, so Michael has a really quick solution. Just spend enough money to buy MATLAB and, and you've got it. How much is MATLAB going for these days? Does anyone know? It used to be at least 1,000 way back when. I don't know what it is now.
You can solve problems for free online somewhere.
Something like an online version of Mathematica, or?
Oh, there is Octave, right? So
there's more than one. Yeah.
Okay.
The Octave is free, literally free, and as far as I'm told, if you are as beginner as I am, they are undistinguishable.
Okay.
Yeah.
Okay. Well, consider you're interviewing for a job at one of these places then. So what would your approach be to adding two polynomials, the way these particular polynomials, the example that he's given? how would you represent the polynomials in the first place, and then how would you use that representation to add them?
Well, if you're asking in real life, and if I didn't have a library to do it,
Mm-hmm.
I probably wouldn't use a list. I'd probably use some type of map or hash map structure.
Mm-hmm. What would be in the map? What would you store in the map?
The coefficients of a term. So every node in the hash map would be indexed by its coefficients and would have it would index by its the exponents. And you would want to keep the coefficient in the hash map. That's the way I would solve it in a language like
how would
Java.
you represent? How would you represent the exponent? So the key for the map is the exponents.
Well, okay, yeah. So you would need a key. You would need a key. Well, how big could your exponents be? If they could be,
yeah, you can make some reasonable assumptions.
If they could be less than 255, then you just take that. You just take those bytes and you make that your key. However many bytes that is. If you've got 4 variables, then your key could actually be packed into an integer. If you've got more, then you have to make some kind of array or string. The best if you had polynomials that were that complex, you wouldn't want to use a string for your key. You'd probably use a byte array of some kind.
And then
I'm just talking off the top of my head.
Yes, that's absolutely the intent that I have, is to just get your first sort of gut reactions to how you would solve this. But then how would you add them, Michael?
How would I add them?
Mm-hmm.
Well, yeah, I mean, this pretty similar to how you would merge hash sets. You need to the only you go through one, your smaller one, and if that key doesn't exist in your answer, you just put it in, and if it does, you pull it out and add the coefficient and put it back.
Okay.
Yeah. And in fact, I did a little tiny bit of reading ahead. I cheated. And I think he's going to do something very similar to that, just using a sorted list instead of a hash map. But yeah, you just need some sort of data structure where you can merge things the way Michael was describing of walking through both of them and being able to say, are these the same coefficient? If so, I'm going to add them together. Otherwise, I'm going to handle one of them and go on, handle the smaller one and go on until I've gotten to the end. And you could do that with a sorted list or a sorted vector, or any sort of linear data structure, really. I think if I were doing this in C++, having seen his answer, having not seen his answer, I would be like, what's the problem? I'll just bang on the keyboard until I, start running into problems, and then I'll solve them. I haven't seen a problem yet. Yeah, I mean, I think a couple of sorted vectors is actually a good representation of this.
So it would be 2 vectors of the same size where the position is the exponential?
No, you would have the same thing he's about to do with lists. You would have a single polynomial is represented by a vector of terms, where each term is identified by it's all of its stuff, right? 3x squared plus y or whatever. But then you would sort those by their exponents. So if it was...
So I was trying to thinking when you have 2 polynomials of different sizes. So you can have holes, right? Like one polynomial, like the example is given. One is it's bigger than the other one. And to be able to match the right, you need to match the right exponential with the right exponential to add them, right?
Yeah.
Right. Let's see.
You're not adding the elements of the vector element for element. What you're doing is merging them. So you look at lowest element from each vector, and if the coefficients match, you output the sum of the coefficients. Otherwise, you output the lower one.
Yeah.
And then pick from whatever list that lower one came from. It's just a merge, just exactly as if you had two sorted lists and you were trying to merge them.
Okay, well, I think that's pretty good. We have a couple of different approaches here, and one of them is very similar to what Knuth offers as the algorithm. So let's read that. This page, just continuing below that problem description on to the next page, to the end of the algorithm. We have about 7 minutes till 2:58. Does anyone need more time? Okay. Who can summarize?
Which is what Michael was saying, right? Which is merging the two lists, the two polynomials. Oh, let's talk about the data structure. The data structure was very interesting. So, since we do several words, like one big object with a bunch of zeros and ones. So, there is a big chunk for the actual coefficient of each term, and then a plus minus sign for the bit for plus minus, which was very interesting for the Sentinel. And then I guess in this case, ABC is because we are talking about polynomials with 3 variables. If we had more, it would be bigger, presumably. And then the link for the next coefficient. So the next, how do you say term? Is it term?
Yeah, term, that's right. Or node, you can just say node.
You can say what?
Node, because of the...
No. Oh, yeah, but I'm talking in terms of polynomials. But yeah. So from there on, so as you can see how he likes sentinels, as you guys were saying in the beginning. So we have the one thing that is negative is basically the end of the polynomial. So the polynomials have an end. The p has an end, right? It's just p, the one that has a negative. Is it? Yeah. So q doesn't need to have it. I'm remembering correctly. The negative PTR.
No, they're both exactly the same representation.
So any polynomial has an end for the negative stuff. I see. All right. So it begins adding. So I was a little confusing with A1 when it puts the link of P on P, because P points, it says that P points to the beginning of the polynomial, but then say initialize, put the link of P in P.
Okay, what does that mean?
So that's what I'm trying to see. So I think I got a good intuition about the whole algorithm, but that little part confuses me a little bit. So I guess I'm confusing about what P is supposed to be in the beginning. So my understanding was that P was had the address of where the whole thing begins. When we says put link of P on P, it means put the address that is in the subsection of the whole object of P, where
it means go on to the next element.
Yeah. So what happened with the first element? So I thought we were adding, we were putting P in Q.
The first element is the sentinel.
Is it?
Well, I mean, A3 happens over and over. A3 is how we step through this list. And after finishing with one node, we move on to the next one.
If it's a circular list, all we need to do is keep track of the address of the sentinel. And then when we process it, we process the next. Maybe we can delete along the way until we get back to the sentinel. So the sentinel, if you look on the diagram on the book, just above algorithm A, it doesn't call it PTR, it calls it PTR, not P, but that's what it looks like. That element all the way on the right is the sentinel.
Makes sense.
And your polynomial only has 3 terms. So to start processing it, you have to follow the link first.
Do you remember what Arthur said about having that pointer point to the tail? Because then from the tail you can easily get to the head. It's just one, in either direction, one hop. So that's what's happening. We're just initializing the traversal through P.
No, makes sense. The part I missed was that P, initially P was the sentinel. That's the PTR. That's the part I hadn't seen. Yeah, makes total sense.
What about the other steps? Any questions about the 3 things that need to happen when we're merging? There's a possible insertion, there's a possible update, and there's a possible deletion.
Right. So if you add 2 coefficients and they happen to be the result happen to be 0, you just remove the node of the result.
Yep.
Right. You just link to the other one.
Yep. Any thoughts on this? How do you feel? I mean, a couple of you did describe this as a possibility that occurred to you. But if we were considering this versus a hash map approach, any pros and cons?
Well, I think this is more efficient than the hash map idea for addition, and also will be for multiplication, which is just repeated addition. Because here, I think we're minimizing the amount of traversal that we need to do. We don't have to go repeatedly looking things up. We just walk through both lists together.
Yeah, okay, great. Looks like Michael got disconnected for a little bit. Michael, we were just discussing any pros and cons versus a hash map approach. So if you have any thoughts on that.
Yeah, Google didn't like the hashing idea either. So no offense taken.
Yeah. Okay, any other comments or questions about the algorithm?
One thing I was wondering is, did anyone see like where the stopping condition is in this, or is it just implicit? Because I couldn't really figure out like from the algorithm.
That's a great question. If I understand you correctly, you're asking how does the algorithm terminate?
Right. Yeah.
Right. So who can explain?
Well, so the termination is hiding at the beginning of step A3. If ABC of P is less than 0, the algorithm terminates. And ABC of P is less than 0 only if it's -1, only if it's the sentinel.
Got it.
So only if we get to A3 with P at the sentinel do we terminate, and that only happens, you only ever get to A3 if P and Q are in the same place, that is if they're equal, and that only happens if Q is also at the sentinel.
Yeah, so what I found interesting about that is the basic premise that he's made, that the sum, the result, is a modified Q. So we're not really constructing a different, polynomial. So essentially, we just have to traverse P. And when we're done with P, then whatever is left in Q is the result. That's how I understood it.
Although it wouldn't take too much modification to have this just copy the nodes. It already has to sometimes add nodes sometimes remove nodes, which we would just say don't copy, and sometimes it traverses over nodes without modifying them, in which case we would just say, okay, make a copy of that node.
Yep.
You could easily modify this to make a copy. But,
Okay, so let's take a break till about 3:16, and when we come back, we'll do the next algorithm, and hopefully we'll have a lot of time for some exercises. See you.
Ya está. Entonces,
Well, I guess it's basically saying that if you modify algorithm A in the particular way it says in step M2, then you can just do that for each term of the polynomial. So rather than just adding one copy of Q to P, or adding one copy of P to Q, instead you're going to add X copies of P to Q, where X is the coefficient of the current term of the multiplication, right? So you have a multiplier that's a whole bunch of different terms, and you're going to take this term and start accumulating that many copies, and then move on to the next term and accumulate that many. It's multiplication. It's how you would do multiplication if you were doing it by hand.
I actually still don't understand what happens. So I to be honest, I don't understand anything of it. Starting at the beginning, it replaces the polynomial Q by polynomial Q plus polynomial M plus polynomial P. I'm still trying to make sense of that first and the.
That's true. It is not really doing the same thing as the previous algorithm. Algorithm A was replacing Q with Q plus P. And we called that addition. And so you might think that a multiplication algorithm would replace Q with Q times P. Mm-hmm. But in fact, that's not what he's doing. He is instead now making this a 3-argument function and saying, let's say we have polynomial P, and then we have this other polynomial M, and we're actually going to multiply P by M and accumulate the result into Q. So,
but then in M2...
So for algorithm A, we were replacing Q by Q plus P, that is by Q plus 1 times P. Mm-hmm. And now we're replacing Q by Q plus M times P. And so the changes that we're making here are basically the changes you need to turn a multiplication by 1 into a multiplication by M. Where M is a...
Oh, okay, no, wait. I missed the quotes. So it's saying, replace, open quotes, if AVPC minus 0 is less than 0, then minus 1, otherwise plus, with whatever coefficient P appear, then multiply. I see. So where is Q coming to this? But so, why are we adding Q at all? Shouldn't we multiply first and then Q? So what?
Remember, Q is not part of the multiplication. Q is just where we're accumulating the result.
So basically, we'll start with an empty, possibly an empty polynomial. It's just a PTR for Q. And we're
going to have something already. It doesn't matter.
Yeah, it wouldn't matter. If we only want to multiply 2 polynomials, wouldn't just start with Q empty or something like that? Okay, if we are putting
an empty list consisting only of a sentinel with value -1, right? It literally will use 1 word of memory, well, 3 words of memory, but it's an empty list.
So basically, is making the fact that with addition, we are going to store the data in Q. So where to put the results is provided by the addition, essentially. And then the actual multiplication happens in the, and the rest of the steps is still saving stuff to Q. So that's what I thought, that we will begin with just the PTR of Q, because in the A algorithm, if something is not there, basically, if you're doing just the A algorithm, and P is a regular polynomial, and Q is just the PTR, the empty polynomial, you will end up with just P, right, in Q, which will be just traversing P to Q, in addition.
If
so that's what they're doing in the multiplication, making use of that for some reason.
If
right?
M is 1, then you will have exactly 1 times P being added to Q.
Yeah.
But M can be a polynomial with multiple terms.
Yeah, because in this case, we don't... Wait, but for multiplication, we don't... Polynomials... They don't need to be the same. You can multiply... You multiply everything with everything.
Well, and also it's a lot harder to compute that product if you're modifying one of the operands, one of the 2 operands, the multiplication, as you go. Because you're going to start adding terms, and then you're going to forget which of those terms you added and which ones were already there, and you need to multiply those.
No, actually, I don't know whether that's true, because they're sorted, so you're always adding terms that are bigger than the ones that you're looking at, I think. But you're right. I mean, what surprised me about M is, well, A was just adding Q to P and in place. And then M is still replacing your polynomial in place, but adding the multiplication of 2 new polynomials, M and P. So Q is still replaced in place, but that's why the add works, because you're really adding it, but you're just adding the multiplication of 2 polynomials instead of just 1 polynomial.
Right.
I think it's cheating.
Q is still an output, but it's no longer really an input. I mean, technically, yes, we're doing adding here, but adding is just a single traversal. We're not doing anything interesting with Q. I mean, the important part. It means the sentinel stays the sentinel. If you put in -1, you get out -1. But if you put in anything else, you get out that thing you put in plus ABC of M. And he's saying, basically, we're going to do the multiplication of this term by that other term, this term in P by that term in M. We're going to do that multiplication, which means adding their exponents, adding their ABCs. But if one of them is the sentinel, then don't do that, because the sentinel is not really a term.
So he's saying that hold on. So it's saying it's literally saying that take algorithm A. Every time we see ABC of P, replace that with the result of if ABC is less than 0, put -1, otherwise add addition. Like literally that, like the result of that, right? Is that what that means? So ABC of P is that's like super clear. Mm-hmm. And then the new node becomes the addition of the coefficients essentially, and that's what you add with Q, which is where you're actually not adding, you're just putting it there. That's what you're doing. So you're multiplying, you're adding the coefficients, and that the result of adding those coefficients become. And also, so you multiply the coefficients and add the exponentials, and the result of that new node is what you would add to Q, quote unquote, add to Q, basically save to Q. Is that what? I think I get it. Yeah.
Yeah, I'm not sure what that figure 10 goes with, though. Yeah. Okay. And figure 1 that it's referring to there is on page 273, by the way. I mean, I think this is another one that wants you to write code for it, basically. Otherwise, I think the algorithm is just walk down the list, keep 2 pointers. He said this 2-pointer idea would come back several times. Yep. And step forward, and as you go, swap the direction of the existing pointer. It could be. Do we have an existing algorithm that shows how he's dealing with these PTRs in MMIX? I'll put the additional wheels up there, I think. The program A, I think, in the MMIX book, your polynomial. Yeah, but it uses the same representation. And it shows that he has the thing we're calling PTR coming in as basically some named register, which we could just call P. Yeah, that sounds right to me. That is an interesting question. Yeah, I guess that would work fine. It would just sort of always go immediately to step A3, and it would add the coefficient to itself and advance both pointers and go around again. So yeah, I think that algorithm A would work fine if P equals Q. However, algorithm M, I claim, is definitely not going to work if M is equal to Q. Or he's asking about all three. He's asking about all three of them, right? And I think 2 of them are definitely not going to work. If Q alias is one of the operands, then we have trouble. And P just fine. Well, multiplication is commutative, so P and M should be treated the same way. Right? I mean, if P can alias Q, then M should also be able to alias Q. But I think neither of them can alias Q. Can they alias each other? I think yes.
I don't think it works if Q is aliased to anything, because on the first pass of multiplication, Q is going to have things added to it, and then on the second pass, because Q is having things added to it, you're adding things to M or Q, whichever M or P, whichever one is the same. You see what I'm saying? If you let Q and M be this. Multiplication is going to use several passes. On the first pass, you're okay. But on the second pass, you've got the added terms that you added to Q on the first pass, and you're multiplying them. You're now the polynomial that you're multiplying by has also gotten them added because they're the same thing. If P equals Q, then when you go through the first multiplication pass, you're okay. But on the second multiplication pass, Q is going to pick up everything that you added. P is going to pick up everything that you added.
So after the first pass, Q has all the elements of P multiplied by the first term of M. Right?
Multiplied by the first term of M. No, yeah. It's got more than that. It's got more than that because remember, we're adding to it. So if Q could have, well, actually, you think of it as Q starting out with nothing, but then you'd be Yeah, that's a good thought experiment. You think of it as Q having no terms. That's the way you multiply M and P, right?
Yeah.
After the first pass of multiplying by the first term of I guess it's the first term. I don't know. I don't remember which one is first. Then now Q is no longer empty.
Now Q has P. So your assumption is just broken, basically. You had assumed that you were adding by nothing, but now you're adding by something that you had before. So probably the algorithm works in the sense that doesn't blow up, but the result is probably not the right one, right? Because I agree. So what you're saying, Michael, is that if your assumption is that Q is something entirely different, either another polynomial or an empty polynomial, but they happen to be the same address on P, then therefore it's P, it will work if that's what you wanted to do. If you wanted to add P plus P times M. But
actually, I take that back. The one case where it does work is where Q is empty, because if Q is empty, then P is empty, and you're going to multiply empty by M, and you're going to get nothing. It's going to terminate on the first step, and that's the correct answer. But if if your Q started out with one element, let's say, yeah, that might work too.
So, no, but for the case of P equals Q, what I'm trying to say is, what I'm trying to imagine is, if M is equal, if P is equals Q, what would happen is that now Q has all the values of P. So we say that the addition in that case sort of work. So it would be equivalent to say P added by P plus M. If that's what you wanted, that would work, right? You will get the result that is the equivalent of that, I think. But if it's not what you wanted, you will get the wrong result. You won't have P times Q. You will have P times Q plus P. Is that right?
I think you get into trouble with the second term. Because
I probably recommend writing this stuff down. As soon as you start lose track of which one is P, which one is Q. If you write it down, you'll see how it works, I think. Write down the statement you're trying to make and then see if it makes sense when it's written down.
So I'm just trying out some different examples with either M equals P or P equals Q.
But remember, when you're writing these down, that's just a symbolic representation of it, and that really...
yeah, we're talking about the exact same, identical thing, yeah.
That's why it means a pointer to a node that has...
right.
So what I'm trying to see, so actually this would be much better if we all were in the same room with the whiteboard, obviously. But so let's say that you literally just want to take a polynomial and add it to the result of multiplying that very polynomial with another one. So I'm trying to see if in that case making P equals Q will do something with it. Because I agree with you. I mean, the several passes thing makes sense, but wouldn't that be the expected result? Like, if you wanted to do P multiplied by added to P plus Q plus M, and instead of having P in two places, you have the same address in both, like using Q at the same address as P. Would that give the right result? If you wanted to do this, and if I'm making sense. Like, at purpose, you wanted to do that.
So that's aliasing P and Q.
Yeah.
Does aliasing P and Q always work?
No, I agree. I think it doesn't.
Then can you show an example where...
Oh. No, it's just my intuition. I agree with Michael. It seems like if you're aliasing them and you don't want to do what I got, like just literally want to use P 2 times, then you will get an expected result. I don't think it will blow up. It's just going to give you something that makes no sense.
Well, it wouldn't be the right answer, because now every time in that cycle you've got a modified P.
Exactly.
That now you're multiplying, and that's...
Yeah, you're getting something that that makes no sense. Yeah.
Okay, what about exercise 17, which is asking, what's the advantage of using a circular list instead of just a regular linked list with a null, a lambda at the end of the list?
I have no idea. Because it seems to me that he's using this pointer thing as the equivalent to the null. But in a null, but it's like a null with a link, essentially, right?
For representing polynomials, it's very specific to representing polynomials.
Yeah. I don't know.
So yeah, I think one thing that immediately came to mind, which I don't think is what he's talking about, is that this lets you save a register. Because remember, Mix didn't really have a lot of registers, or any, I forget what it did. But this way you go around, and when you get to the end, hey, look, we're right back at the beginning. So that's nice. We didn't have to save off the beginning at the beginning of the algorithm. However, in this case, it's significant that he chose the sentinel value -1, whereas every other node is going to have a positive value, and he stores them in decreasing order. So in this way, since you're doing this sort of merge, when one of them gets the sentinel, the other one naturally advances until it hits the sentinel.
But Arthur, I guess the question would be, what would pose a difficulty if you just used a normal linked list?
If you didn't have a sentinel and you just had a null value at the end, then instead of having the algorithm always compare ABC fields, you would have to have it compare this non-trivial function of P. We have a pointer P, and right now in his algorithm, he compares ABC of P to ABC of P. He'd have to change that, and he'd have to say, now we're comparing, if P is non-null, use ABC of P, otherwise use -1.
So you will be, so with the link is in the same realm of comparing numbers, right? Is that what you're saying?
Right. We're always comparing the contents of the node to the contents of the other node. We don't have to have a special case here that says if pointer is null, do something different. There is no special case.
Just like in a special node just for polynomials.
Or any kind of list sorted in this way where all the nodes are guaranteed to be positive. Okay. If he had chosen a different sentinel value, such as positive 999, then it also wouldn't work. It's very specific to this node being the the least possible value.
Okay, last one, exercise 18. This is also interesting. Devise a way to represent circular lists inside a computer in such a way that the list can be traversed efficiently in both directions, yet only one link field is used per node. So you're still only allowed one pointer, but we want to be able to go in both directions efficiently. And there's a hint.
So the hint suggests some sort of relative address. Some way of computing the previous address.
What do you mean by relative address? He's just saying, I think the hint is saying, use an additional pointer. Use 2 pointers. So you can have any other additional variables that you want, but the structure of the node itself just has one link. So if you want to track something that will allow you to efficiently go in either direction from any node, you can use some extra information. And so Arthur has some spoiler. So the title suggests XOR is involved.
So another part of the hint here is he says you have the addresses of nodes xi-1 and xi. So you have two addresses there. And then, of course, each of those nodes has a next pointer, right, which is also an address. So you have 4 things of information here, 2 of which you're right now using, those 2 nodes. And then you have 2 more things of information inside there. So what can you do with those 2 things of information to get pointers in every direction? Does that help? Not really. We don't even need 2 successive nodes. All we need is our current node and its next pointer. What can we do with that to get not just 1 value out, but 2 values? That work?
If you just have the current node, you automatically have its next. So are you suggesting you can do this with just 1 pointer?
I was thinking about that and then thinking no. Yeah,
oh,
so
okay.
Remember, when I say next pointer, I mean the thing in the next pointer field. I wish he would add like words for these concepts, because I don't have the words. I look in the book for the words, and he doesn't have words either. Right, so we have 2 pointers, and they point to nodes, each of which contains a pointer. So we have 4 pointers total.
Mm-hmm. So now let's say that we're as he says, we're at xi-1 and xi. How do I go back? How do I go back to i-2, which was, the previous node before we got to this pair? So going forward is easy, because that's the direction of the link of xi. We can easily get to xi plus 1. How do we get to xi-2, the node before the first of the pair?
I'm trying to solve it by creating a list, from series. To start with nothing, and you add 1 element, is there. Then you add the next element. When you add the next element, you should be able to get back to the previous one. So
I think adding, to me, sounds a little more complicated way to think about it. Because now if you just think of, like, you're at some pair, how do you get to the node that's before the first of the pair?
So let me go back to what we know. So let me see if I got what we know. You have an object, a chunk of bits, and some of that is, so we have space for a link and space for other stuff, right? So we can only have an address. We only have a space for an actual address, but you were suggesting that we also have a space for other sort of data that is not an address, it's less than an address.
No, you're not. The way I understand it, you're not allowed to store any addressing or link information except for the one that's pointing in one direction.
Okay, so that, for me, that has to mean that you need to be able to compute the previous address from the current one. So there has to be a rule for finding the next address or something.
Well, yeah, I guess the link could be something that could be used to compute that. But you're only allowed to store 1 address. Mm-hmm. I think that's the restriction. You're only allowed to store 1. You only have 1 field that can somehow be a link of any kind.
There, I've put in the chat what the constraints are.
Mm-hmm. the link of xi.
Right. Exactly. So it needs to be, read, but using the address themselves, right? So there needs to be a rule about how to go about it.
Do you mean combine link of xi with link of xi plus 1?
Nope. I mean, what I wrote.
Here's what you do, okay? If you had a forward link list, you would have one value in that link. And if you had a backward pointing list, you would have another value in that link. Instead, XOR those two addresses and store that in the link. That doesn't point to anything, but that in combination with the previous address points to the next address.
Yeah.
And that in combination with the next node's address points to the previous address.
Yeah.
That's the property of XOR. So that's all it is.
Yeah. So I guess what Arthur means over here is these are the 2 pointers that we have. You know, when you say xi plus 1, we're getting that from one of the pointers, and then we can use that to produce x of I minus 1.
Yeah, it's xi plus 1 and xi minus 1.
Mm.
And then you also know which node you're at, and if you address of x plus 1 and address of x minus 1.
Yeah.
Together with the address that you're currently on. What you store in the link is the XOR of the node plus 1 and the XOR and the node minus 1.
Yeah. So you can so maybe you can give them names. These 2 pointers. There's like P1 and P2, and then they have those specific values that you would use to XOR with the stored link.
Google is not being my friend today, or Google Chat.
Okay, great. So so we're done with the exercises. So if you guys can stick around, that'll be great. I am now going to. Oh, first let me show you what is planned for next meetup. So the first thing is Thanksgiving is coming up, so we're going to have Thanksgiving off. There won't be a session that weekend, which will be the following one after the 21st. And the way I see it, I think we're good to start sorting, at least some sections of sorting, because we really just need the sequential allocation and the linked allocation concepts for quite a few algorithms in sorting, and I think we can start that. So I'm pretty excited about that. And we'll start with the first section next weekend. And I think that we can cover about 10 to 12 meetups just for sorting. And then we're going to come back to volume 1 and continue with these other sections, and we'll get into trees. I think that's coming up in like 2 or 3 sections in volume 1, but yeah, for the next few meetups, we should be using volume 3. That's what I hope that we won't run into any unforeseen things. But if we do, we can always, consult something to get those prerequisites out of the way. So, any thoughts or comments on that? Everybody good with that? Sound good?
Oh my God, I put in the chat.
I'm sorry, I didn't get that, Arthur. I see. You won't be here.
Weekend.
Oh, but you could do Thanksgiving. Okay. Can people do Thanksgiving? The Saturday after Thanksgiving?
I mean, I don't care.
So you're okay with it, Miguel? What about you, Michael?
Yeah, I'm fine. Either way.
Let me think about it. I should be able to say one way or another by tomorrow. So I'll either post a message saying if we have something or not, or I'll just schedule it. So yeah. Okay, so I will do a walkthrough of program A from the supplement in MMIX. Here's the link to the source in GitHub, in case you didn't see it on the Meetup page. And let me adjust the window. Okay, how's this size? Is this, can you see the values in the bottom panels, the memory windows? Okay. Let me see if I can make this a little bigger here. Okay, so the layout of the node is a little different in the actual program than what was described in the text. The exponent field seems to be using or allowing for 4 variables. Because what he's done is just use 1 bit for the sign. So that's going to leave 15 bits for the first exponent, or the exponent of the first variable. And there's a couple of interesting things here. So the first is the representation of the 3 polynomials. 2 polynomials, P and Q. The third one is the result. That's also hard-coded for comparison and verification. So over here, this is polynomial P. And what's happening is that P has 1, 2, 3, 4 terms, right? It's 5xy plus 7x plus 7yz plus 20. So the first polynomial, the first term is actually here. This is the first term. So it has the exponent for x and y, which is 1 and 1. So that's this piece over here. So these are 16 bits wide. And then the next two variables are not in that term. So those exponents are 0. And then the coefficient is the third octa. So there's 3 octas here, right? So there's this first octa, which is the link, the second octa, which is the ABC field or the exponents, and this is the third octa. And so that's the first term. So the way, if you remember, these local symbols work is that if you have a reference that has a number and then an F or a B afterwards, it's referring to a symbol that's either defined below or above the current statement with that same number. And so since this is an F, 1F means the closest 1H after this statement. And so that's this 1H over here. So what's that saying? That's saying that this is a reference to the address of this octa, the first octa here. And that's the link of the second term. So this is the way the first term is pointing to the second term. And similarly, the second term again says 1F, which means we go forward and we look for the 1H that's closest, and which is, you know, right afterwards, and that's the 1H. So Arthur is asking, syntax highlighting treats semicolon as
yeah, I mean,
yeah,
has like 3 octas on it.
Right. That's yeah. So that that's because yeah, if you didn't have the semicolon, then that would be a comment. So it's I think it's a bug. The bug in the Visual Debugger syntax highlighting. If I didn't have this semicolon, then this is definitely a comment, but yeah. So then we have this first node pointing to the second node pointing to the third node. And the third node then points, or the third term points to the fourth term. This is the last term, but notice that this points to P, and P is fixed over here, right? The P symbol is the address of this first octa, which is actually the sentinel, that special node. So even though, you know, in our diagrams, we've seen sort of the sentinel, or we think of the sentinel as being at the end, but the way they've declared or defined the memory layout here, or the data using the MMIX assembler features, it needs to come before these. Actually, I think it can even come after. Yeah, I think it can come after, but then it's problematic because then we would have to have like a 1B here. Yeah, I think it could come afterwards as well. But yeah, so this is interesting. And then the same thing happens with the other polynomial. Polynomial Q is 3xy minus 7yz plus 3y minus 20. So it's got 4 terms. And these are the 4 terms from line 47 through line 50. And then line 50 points to the sentinel Q. And this S is what we expect the sum to be. 8xy plus 7x plus 3y. There's a little piece of code that can compare 2 polynomials and check for equality. down here, we've got the storage pool. So it's just a fixed number of nodes, and it has this address free as the starting node. And then there is the avail symbol, which is associated with one of the global registers. So we expect this to remain available in all contexts. It's initialized to 0 over here, or declared as 0, but it's initialized at the beginning of the program to be this address. So that's how the avail list is working. It's basically going to take nodes or memory locations off this region and return them back here as well, adjusting the pointers as needed.
So I am actually about that, because here we've got basically a linked list of octas, like single octas that are all linked together.
No, there's 3 octas each here.
Oh, okay, so that's syntax what the commas means.
Yeah, the commas allow you to use a single directive for multiple values.
Okay.
And over here, we needed the semicolon because we were breaking up the middle octa into a wide. That's why we needed a different, directive.
Okay. Okay, I buy that then.
So, okay, so that's the setup. Then there's these constants over here referring to the offsets of the fields. So coefficient is what we expect. That's 2 octas off. And ABC, which is the exponent field, that set of wides, that's 1 octa into the node. And link is the first octa. So those are the offsets. These are the 2 registers that will be associated with the 2 polynomials. P is $0, Q is $1. That's just bookkeeping. And then these are the 2 tracking variables that we need for the various operations. And again, this register will hold the ABC, the exponent value. Coefficient of P is in this register, coefficient of Q is in this register. This is a temporary variable. So that's pretty straightforward. Okay, so we go down here and we're going to start at main. And as I said, the first thing is we initialize the available list to that region that starts at free. Then we start using it. We load P, the address of P, into $1, load the address of Q into $2, and then we push jump, which is the call to the subroutine add. So add is going to get these 2 registers, because we said push jump $0 means that we're not saving any register. So everything above 0 is going to be available to the subroutine that's being called starting from 0. So whatever's in $1 here gets passed to add as $0, and then so on. All right, so let me now let me just show you add as well. So here is add, and yeah, let's just step through this. So okay, start at main. Let me get rid of these windows I don't need. All right, thanks, Arthur. Oh, you said 4:30, so I just noticed. Cool. All right, so what do we have here? We are now at main, and let me step into add. Okay, here we go. So now we're at add, and we're initializing the Q and the P registers with the with basically the addresses of the first terms of each polynomial here. And we're setting the coefficient register. So we're now going to start traversing P. So we get the coefficient value, we get the ABC or the exponent value into these two registers, and then we start the main loop. What we want to do, if you remember, is we want to compare the exponent fields. So this register now has, after this statement, it'll have the exponent field of Q. And then we already have the exponent field of P in ABCP. So we're going to do a comparison, and comparison will return positive, negative, or 0. So let's see what happens. The first term, let's go back over here. Let me actually type that in here so we can keep track of that. Adding Okay, so when we do the comparison, first terms have the same exponents, 1 and 1. So we should get a 0 for the comparison in register T, which is $7 over here. So we can see that. So they're equal. 0 means that the two terms need to be added together. And so we're going to branch to A3, which is down here. And then we have an additional check at that point because we need to make sure that they're not comparing equal because, you know, it's the sentinel. So if it's the sentinel, we're done. But if it's not, then we do need to add. In this case, it won't be the sentinel. So we add the two terms. And adding the two terms means adding the coefficient of both. And so that's what's happening here. And then once we have that sum, which was 5 plus 3, which is 8. So $6 is showing 8. That needs to be written back to memory for Q. Remember, Q is being modified in place. So that's going to hold the result polynomial. So we do that, we store it, and then we need to go back if the sum is non-zero. Because if the sum is 0, then that means that term has disappeared. If the term has disappeared, then we would need to delete the node. But if the sum is non-zero, which is the case here, the sum was 8, then we essentially need to go back to where we were in P and start moving to the next term. So that's essentially going to take you back to the beginning of the subroutine. So that's what this branch is all about. And let's see, what else do we need to be careful about here? Oh, yeah, so down here, actually, let's see where Q is being modified. So if we go back to P and Q, when P was declared over here, it got the address at that point in the the memory layout that the assembler is generating. So this actually started out at the beginning of the data segment, right? So the data segment has this address, and P is the first symbol associated with a memory location. So it will have this same address. That's the sentinel node of P. And then P, we saw, has 1, 2, 3, 4 terms. Each term, which is one node, takes 3 octaves. So 4 of these means 12 octaves. And if you add 12 octaves to P's address, that will give you, actually not 12. It needs to be 5 times 3 octaves, because there's the sentinel node as well. So P has now occupied 5 times 3, 15 octaves. So if you add 15 octaves to the address of P, then you should get this address. This should be the address of Q. And so down here, this is the beginning of the data segment. So this is the address of P. So what we should be seeing here are basically the nodes of P. For Q, let's modify this second panel so that it starts at 78. And so this is the address of Q, the second panel. And I'll explain what we will see in the third and the fourth panel. In the fourth panel, I've got this address, the bottommost panel. This address is the address of the storage pool, the beginning of the storage pool. So down here, we're seeing all the nodes that are going to be used to allocate new memory. And then any nodes that are freed are again going to join the available list down here. So avail will always have some address here. Okay, so now if we go back to where we were, when we add, we've added the 2 terms from P and Q. So in this second panel, remember this is the memory for Q, we should expect to see an 8 in the first node after the sentinel, right? So this is the sentinel. You can see that this is the link for the sentinel. This is the -1, the middle octa of the sentinel node, and this is the 0, which is a 0 coefficient for the sentinel node. And this over here is the link of the first term of Q. These are the exponents. You can see that there's a 1 here, and then there's another 1 in the second wide. So those are the exponents. And then this third octa is the coefficient, and you can see that there's an 8 here. So that's the sum of those 2 terms that got modified in place. And you can also see that the third node, which we currently haven't touched or done anything with, this should be the second term of Q, which is -7YZ. And if you look at this, you've got the link for the second term. You've got the exponents for Y and Z, 1 and 1. And then you've got this negative number, which is -7. Okay. So then you can see the rest of the terms as well. So let's just step through this, and we go back to the beginning. We've got Q1, which is the trailing pointer for Q in case we need to delete something. And then we update Q, we update P, we do the same thing again. We enter that loop. This time around, we are now at the second term of P, which is 7x. And we do the comparison with the second term of Q, which is 3y. So 7x compared to 3y, because x is the first variable, it has exponent 1, which will be bigger than the exponent for y, right, which is the second variable. So the ABC field of P will be greater than the ABC field of Q, and then in that case, we will need to add or insert the 7x term into Q. So that's the behavior at this point. That's what we expect. So let's see if that actually happens. So step. And then at this point, we've got the comparison turned out to be non-zero, and now we expect the comparison to be positive, which means that the branch should occur to A5. So let's do that, and that's exactly what happened. And at this point, the code for inserting a new term will get executed. So let's step through this. So how is that going to happen? We need to insert a new term, which means in our linked list, which is Q, we'll need to get a new node, and then we need to set the values in the new node, and set the pointers in Q, and then we'll have, you know, a new term in Q. So this is what's happening at line 176. We got a new node, and now that new node is referenced through register Q2, and we're now setting the coefficient field for Q2. So we saw over here something turned red, and this is, remember that this third panel is showing the storage pool. So what that's saying over here is that this is the node that was returned by the avail list. And now this node down here is essentially being used for Q. And what will happen is that different fields in this node are going to be set. The coefficient field was just set. It's a new node being inserted from P, which was 7x. So the coefficient is 7. And then the next thing that should happen is that this memory location should have the new exponent value. So that should turn red, and which it did, and you can see that the exponent for x has become 1. So that's what happened here. And then the next thing that needs to happen is we need to adjust the pointers so that it's inserted in the correct location in the linked list for Q. So that's where the two additional registers Q1 and Q2 come into play to adjust these pointers. And then we just go and advance P, meaning we go to the next term of P because we're done inserting this new node. So remember, in this case, when you insert a new term, you don't want to advance Q. So Q needs to stay fixed on the current term because the most recent term that we handled, which was from P, was greater than the current Q term, and we still need to see if there's going to be any other terms from P that can get added to Q that have the same exponent. And at some point, we would expect that we would move past the exponent that corresponds to Q. And then when that happens, then we can advance Q. So the next P term that's going to be handled is the third term of P, which is 7yz, plus 7yz. So plus 7yz, and the current Q term is minus 7yz. Those two terms will actually cancel each other out. So when we do the addition, we'll end up with a 0 coefficient, which means that we will need to delete something from Q. And so that's what's going to happen for this term. And then at this point, we're still doing the comparison. We do the comparison, and in register T, we have the result, which is 0, meaning that the two terms compared equal in terms of the exponent. So now we have to add them. So we go to A3, and it gets, then we do the addition. And after the addition, we check if the resulting coefficient is 0. So if it is non-zero, we would go back to the beginning of the subroutine, but in this case it is 0, so we're going to fall through, and so then we handle the case where we found out that the coefficient is 0, meaning a term from Q needs to be deleted. So that's what's going to happen here. And so to delete a term, or to delete a node from the linked list for Q, two things need to happen. One is we need to return, we need to basically adjust the pointers of Q so that they're no longer referencing that current node, and then we need to return the node to the available list. So this is the adjustment that's being made on line 160 to the current nodes in Q. And once that is done and we store the update to memory, we return the node to the available pool. And returning means that whatever node we return, that goes to the top of the available pool, and avail just is now pointing to this newly returned node, and the next time a new node is needed, this is the node that will be used. Okay, so that's done for the deletion. And then because the term from P was used, we need to advance P, and the term from Q was deleted, so we actually don't need to do anything at this point with Q, because it'll just automatically get updated to the next node. So do that, and we advance P. Now we're at the fourth term of P, which is just the constant 20. And so we load the exponent field In $4, you can see all zeros, which means that it's constant. And we do the comparison. So the 20 is now being compared to the fourth term of Q, which is a minus 20. And then these will turn out to have the same exponents, which means that they'll need to be added. When we add the 20 to a minus 20, we will get a 0. And so again, we will need to delete a term from Q. So let's see if that's what happens. We do the comparison. Oh, no, that I misspoke. The term that we're looking at right now is actually the third term of Q, because we had not processed that before. So remember when we added plus 7yz to minus 7yz, which resulted in a term being deleted from Q, then the next one is actually 3y. So this is the case where 3y is being compared with plus 20 from P. And that means that the Q term will have a higher exponent, right? Because y is present, and the term from P actually doesn't have any variables. So the comparison turns out to be negative, which means that we are at a term of Q that has a higher exponent than the term from P. This means that nothing needs to happen with Q. There's no modification that's needed, because we just need to go past this term now, right? In P, we've already reached an exponent which is lower. So now we need to advance Q. So that's what we should see here. The P term is not bigger than Q, so we should fall through at this point. And in this case, we just need to update the trailing pointer to become the current node, and then we need to update Q itself to go to the next node, and we go back to the comparison, right? So P stays fixed. In this case, P is not going to advance. So we do the comparison. This time, the comparison is happening between plus 20 from P and minus 20 from Q. And the exponents will be the same for this comparison. So the two terms will need to be added and they'll cancel out. So let's see if that's what happens. So do the comparison, and the comparison result is 0, so they're the same exponent. We go to the, we need to check. Whenever we have two terms whose exponents turn out to be equal, we need to make sure that it's not the sentinel node. And as long as it's not the sentinel node, we can do our arithmetic. So that's what will happen here. We add the two terms. We know the result should be 0, and that's what we see here in register 6. The result is 0. That's the sum of the two coefficients. We check if the result is non-zero, because in that case we can just go on to the next term, having added the two terms. But if the result is 0, then we have to do what we did before, which is to delete the node from Q. And so that's what will happen here. And we've gone through this code before. We update the links, we return the node to the avail storage pool, and we advance P. Right, so we've already processed the node from P that happened to be the last node, which means that at this point we should be at the sentinel node. And we load the coefficient from P, we load and you can see the coefficient was 0. And now we're going to load the exponent, which should turn out to be -1. And that is indeed the case. $4 is -1. And then we enter the comparison block, where we compare the terms from P and Q. And in this case, when we do the comparison, we will end up with this check on the exponent of the term from P. And in this case, we will find out that the exponent was negative, and that means we're done, right? We've reached the end of the linked list for P. So we go to the return from the subroutine, and we go back to main. There's no registers over here because no main didn't save any registers, so there's nothing to show in terms of things being restored at this point. And then there's a little bit of code over here that will compare the Q polynomial with the polynomial S, which is just for the test case. So we've hard-coded the expected result and represented it back up here as this polynomial, 8xy plus 7x plus 3y. And then there's a bit of code down below that does the comparison. It basically goes through the two polynomials and checks if the coefficients and the exponents are the same for each term, and it returns 0 if they are for success, and non-zero if not. And so that's basically down here. This is not really part of the algorithm. This is just for testing the test case data. So I'm not going to explain that, but you can look at the code and try to understand it if you're interested. But what we will see is that this compare subroutine is called, and let me just step over this, and what we will end up with is a comparison for each of the 4 terms and you can see that the branch non-zero was not taken, which means that what was returned was 0, and the program halts. So that takes care of that. So relatively straightforward. I think what was interesting was really the representation of the two polynomials using, the local symbols feature that makes it really convenient and easy to store or to use a linked list in MMIX. And so that is about it. Thanks a lot, and see you next time.